Hey everyone, I just want to go over how we derate our conductors based on number of conductors in contact with each other and based on ambient temperature. And where we're going to see the rules concerning that or regarding that is in section 4 of the Canadian Electrical Code, rule 4. And we're just going to kind of go through some of these rules. I'm not going to go through every single sub rule that's within here, but there is a lot of good information in there. I totally recommend that you look at it. Okay, so I'm going to start right here at subrule 1. Now, subrule 1 basically states the maximum current that a copper conductor of a given size and insulation, right? So whether that comes into play is the temperature rating, is permitted to carry shall be as follows. And I'm going to jump right down to item B here. 1, 2, or 3 conductors in a run of raceway or 2 or 3 conductor cable as indicated in item D, except as indicated in item D, as specified in table 2. Right? The reason I'm jumping down here is I just want to show you how we're doing this when we have more than 3 conductors. The first one here just talks about table 1, and that's for single conductor. I want to focus on when we have more than that. So just quickly looking at table 2 again. So table 2 is for copper conductors, right, of not more than 3, and ambient temperature is based on 30 degrees. So on our left column here, we have our wire size, so 14, 12, 10, and so on. All right. Along the top row here, we have the millimeters squared, like the diameter here. But what I'm more concerned with for what we're going to do is the insulation temperature rating. Right, so that's what these are here. This is what these temperatures are here. That's the insulation temperature rating. Whether it's a T90, so an NMD 90, T90, TW 75, NMWU is good for 60 degrees, right? So that's what these numbers are here. So for example, say a number 10 T90. So if you're using a number 10 with a 90 degree insulation rating, temperature rating, we can see that it's rated for 40 amps. It's permitted to carry 40 amps. Okay, but that is good for up to 3 conductors. And I should mention too that tables 1 to 4 all deal with conductor ampacity, but tables 1 and 3 are for copper, or sorry, tables 1 and 2 are for copper, and tables 3 and 4 are for aluminum conductors. Okay. And it also mentioned in this item here, except as indicated in item D. So I'll just quickly look at item D. Item D is for conductors but for 1/0 and larger. And just like tables 1 to 4, they give you ampacity values, but based on a configuration of installation, and they're for underground. So if I just go look at one of these diagrams, so say detail 2, where you have 2 cables per phase, so it's like parallel installation here, line 1, 2, 3, ABC, right? You, in this situation, for 1/0 and larger, you would reference another table, right? So I said we're going to use detail 2, and we have 2 conductors per phase. So say I was using a 2 watt. Well, in that configuration, those conductors are good for 304 amps, right? So that's what it's saying. So when you're 1/0 and larger, right, you're going to go look at this. Anything else, we're going to look at tables 1 to 4, right, which are only good for up to 3 conductors. But when you have more than that, then we get to here. Right? 4 or more conductors in a run of raceway or cable, right, as specified in table 2, with correction factors applied as specified in table 5C. So whatever values we retrieved out of table 2, if we have more than 3 conductors, we have to take table 2 values and correct it based on table 5C. In table 5C, simple table, right? On the left, you have the number of insulated conductors that are together, whether that's in a raceway or a cable. And then along that same row on the right-hand column is the correction factor that you would apply. So notice if you have 1 to 3, well, then it's basically 100% of whatever table 2 says or whatever table 4 says, depending if it's copper or aluminum, right? But after that, then yeah, you really got to start derating. So 4 to 6, basically you're only allowed to use 80% of whatever you got out of table 2 or 4. 43 and up, well, you're using half the value of table 2 and 4. Okay, so let's go look at a couple examples here that I've created. We're going to do 4 examples. The first 2 are dealing with number of conductors. I'm just going to start at number 1 here. Okay, so the scenario is conductors with 1 insulation rating. So the question is, what would be the maximum ampacity? Let's get my pen here. Maximum ampacity of 6 number 6 T90 copper conductors in a conduit. Could be in a cable as well, right? But for me, what I really care about is how many there are, and we have 6. Number of conductors. Right? I want to know the size. I need to know the temperature rating, right, in degrees Celsius, and that they are copper. Okay, that's what I need to know to solve this one. So our first step. Our first step in all our questions is basically going to be, what is our baseline ampacity on that conductor? And where you're going to find that, for this question at least, because it's copper conductor in a conduit, is table 2. So I want to go to table 2 and find out, okay, well, what's the number 6 rated for with this insulation temperature rating? Just in general, what is it rated for? So if I go in the code book, table 2, and I said we had number 6, and that number 6 was a T90, so it had a 90-degree temperature rating. I can see when I line the 2 up, it's good for 75 amps. Okay, so that's your first step. Just find its baseline value. So table 2 equals 75 amps. Okay, but because we have 6 of them, there's another step here. We're not done. Second step, right? We need to derate because of the number of conductors. Table 2 is only good for up to 3 conductors in a conduit or a cable. We have 6. So when you read 4004, right, it tells you got to derate now based on, and for this scenario, table 5C. Okay. So that table 5C came from 4004 1C. Right. 4004 subrowel 1C. Okay. So let's go look at 5C and see what our deration value is. So 5C says when you have between 4 and 6 conductors, you need to derate by 0.8. Okay, we're going to take our table 2 values and only load it up to 80%. Right? So table 5C, 0.8, which is basically 80%. Right? So the next step would be just to solve this. So I'll change colors here on the next step. So let's just solve. Third step. So we're going to take our table 2 value of 75 amps and we're going to derate it by our table 5C value. Okay. And we're going to get our new maximum permitted current. So 75 times 0.8 gives you 60 amps. Oops. This right here, that's our maximum permitted ampacity on this number 6 now. Okay. Table 2 says it's good for 75 amps, but because we have six of them together, we have to limit the current. We have to reduce the current on it, because if we don't, there's going to be a lot of heat to dissipate. Right? A lot of heat on that insulation is going to break it down over time. So in order to protect the insulation, we reduce the amount of current on the conductor, which therefore reduces the amount of heat that's generated from that conductor. Right? So that insulation can now, dissipate safely without breaking down over time. Okay, so that's how we do the first one. Number 2. So this one's a little interesting, and you will see this. So let's look at the scenario first. Conductors with multiple insulation ratings in the same conduit. So multiple insulations. Let's pick apart this question. What would be the ampacity rating of 2 number 10 T90 copper conductors and 3 number 12 TW75 copper conductors. So what's interesting with this one is you got an insulation rating of 90 degrees on one set and 75 degrees on the other set. We're going to go look at section 4, rule 4, sub-rule 14. If I go down here to sub-rule 14, it states the ampacity of conductors of different temperature ratings installed in the same raceway shall be determined on the basis of the conductor having the lowest temperature rating. And if you continue reading on to 15, sub-rule 15, the ampacity of conductors added to a raceway and the ampacity of conductors already in the raceway shall be determined in accordance with the applicable sub-rules. Meaning, just we're going to come back up to here. And this would happen. Say you're on a renovation job and sometimes you reuse conduit, right? Why run a conduit that when there's already an existing conduit there and you have enough room to add conductors? So say there's an existing conduit that's got a couple TW75s in it and you're going to pull in some 90 degree rated conductors, right? You're perfectly welcome to do that. The thing you have to watch out for though is your 90 degree rated conductors have to be based on the 75 degree conductors that were in that pipe already, according to these sub rules. Okay, that's the only caveat there. So keep that one in mind. But either way, let's solve this one. It's very simple. First step, as always, let's go get our baseline values from table 2. Okay, so our number 12, well, we'll start with the number 10 as I read it here. So our number 10 T90s are going to equal, and then our number 12 TW75 are going to equal. Before I write this out, see if you can figure this one out. What are the values of each one? Okay, so we're going to go to table 2. I know that I'm using number 10, so a number 10, and I'm using a number 12. All right. We'll just say that number 12 is already in the pipe. So my number 10 is a T90, but because I'm going to be mixing it with 75 degree insulation, my number 10 value from table 2 is actually going to be 35 amps, not 40. Okay. Oops. We are going to be using this right here, 75 degree. So number 10, 35 amps, and our number 12 will be 25 amps. Okay, so 35 amps, 25 amps. Don't mess this one up right from the get-go because it will affect the rest of your calculations. This, even though it's a 90 degree insulation temperature rating, we're basing it off 75, the lower value, because of this rule right here. Okay? All right. Let's carry on here. Next step. Well, how many conductors do we have in total? 3 number 12s, 2 number 10s. So we have 5 conductors in total. Therefore, we got to go looking at table 5C again, just like our last question. Right? And it will be the same, right? Because when you go look at table 5C, meaning it'll be the same duration value, we have 5 conductors, so we fall right between 4 and 6, so our ampacity correction is going to be 0.8. Right? Table 5C equals 0.8, or we can say we're going to load our table 2 values to 80%. Okay. So now we're going to take these values here and derate them. So our number 10s, which were good for 35 amps, we're going to multiply that by 0.8. Oops, wrong drag. And our number 12, which we said we're good for 25 amps, we're going to derate that by 0.8 and get our new permitted values here. 35 times 0.8 is 28 amps. And 25 times 0.8 is 20 amps. Okay, this is the maximum permitted current that we can put on these conductors in this scenario. And the trick was with this one was we had mixed insulation types in the same conduit. Other than that, it was done the same way as the previous question. It was based off the number of conductors, right? So watch that first part there. Watch, always make sure you're paying attention to the type of insulation. All right. Always go with the lowest value. Cool. Now I want to get into ambient temperature. All right. And again, the whole purpose of insulation, right, is one, to protect you from shock, but it has a temperature rating and it's designed to dissipate heat from that conductor. Right. Well, it can't dissipate very well if it's in an environment that, like our last two examples, is surrounded by other conductors that are dissipating a lot of heat, or, for our next two questions, is in an environment where it's above 30 degrees. Remember, tables 1 to 4 are based on 30 degrees, right? So let's look at that. And before we get into the question, let's just look at the rule, which you're going to find in section 4.004, sub-rule 7, and I'm going to look at B1. Okay. So go down to 7. So again, this 4004 is talking about maximum permitted ampacity on conductor. We're going to go down to sub-rule 7. B. I'll highlight this here. 1. Right there. So ampacity of the conductors out of table 2. Right, they apply it to power and lighting, and it shall be as follows here. So the ampacity correction factors at table 5A, where conductors are installed in an ambient temperature exceeding, or, get this one, anticipated to exceed, meaning if you're installing conductors and it's like minus 10 degrees, it's January, minus 10 degrees, all right, you're just basing it off table 2. But you know, come July, June, July, August, that the environment you're in is going to be, say, around 50 degrees. You have to apply this. You have to derate those conductors. Example, I had a customer that bought a shed, pre-built garage, we'll call it, that was delivered on a flatbed, kind of neat. And he wanted power to it. Great. So I came and looked at it. He just did his driveway. He just put brand new asphalt down. So right away, well, the option to dig a trench to it is not an option. We're not going to start tearing up a brand new driveway. So I went overhead. And to get there, I had to go through the attic of the home. Unfortunately, it was about 50 degrees up in that attic at that time. But even if I installed my tech cable that was going through the attic in the middle of winter, I knew come July, it was going to be well above 30 degrees. So I had to derate my tech cable based on what I figured to be the maximum temperature. In this case, I just said, okay, probably 50 degrees sounds reasonable. All right. I'm not sure how you would get an exact amount. Maybe there's some information on Google, but I felt 50 degrees myself is reasonable. The case is here, or the point I'm making is, I knew that it was going to get warm up there. I knew it was going to be above 30 degrees. Therefore, I had to derate my conductors. Okay. Another example I actually have, and I seen this when I was up in an attic, and the guy had solar panels installed on his home. And the contractor, it was a taller attic, and the contractor put a breaker panel in the attic. It passed somehow, but it passed. But regardless, the contractor, these are all 15 amp branch circuits for the solar panel system after the converter there. They were all done in number 12. And the reason is because of the temperature that was expected to be seen in that attic. So all those NMD 90s, they were all ran in number 12, not number 14, even though they were all 15 amp breakers or ampacity circuits. But either way, If you anticipate that you're going to be above 30 degrees, you have to apply this. So let's go look at table 5A. So table 5A applies to tables 1 to 4. So whether it's single conductor or a multi-conductor cable or a conduit with up to 3 conductors, and whether it's aluminum or copper. So this table here on the left, we have our ambient temperature that we could be expecting to see, and it goes from 35, goes by 5s up to you get to 80, then it goes by 10s. Okay, there's, you know, jumps of 5 and jumps of 10. So what happens if you have an ambient temperature of 42 degrees? Well, if you have an ambient temperature that falls between what's listed, you have to go up to the next higher value. Okay, so if it was a 42 degree environment, you'd use the 45 degree row. Okay, along the top here you have your insulation temperature rating. Right, so that's the rating of the insulation on the conductor you are installing. Okay, there's a little cross symbol here. That's basically just echoing what I just said. The insulation temperature rating is the temperature marked on the conductor. Okay, so for example, if I'm going to install a TW75 and I know the ambient temperature is or expected to be 47 degrees, well then I'd come here and go 50. I'm going to use the 50 degree row. I'm going to go to my temperature rating of the insulation and see that I would need to derate by 0.75. Right, so it's a fairly simple chart to use. Let's go look at our example here. Let's pick this one apart. Okay, so what would be the ampacity of 3 number 10 T90 copper conductors installed in an ambient temperature of 52 degrees? Pretty simple, right? It really is. So first step, like our last two questions, first step, we're going to go right to table 2 and just get our baseline value of this number 10 T90, which I believe was 40 amps. But I'm going to go back and have a look, just to be sure. All right, table 2, a number 10, 90 degree rated, 40 amps. That's our baseline value. Okay, 40 amps. And that is an ugly looking P, so I'm going to do that one over. 40 amps. Okay, that's our first step, baseline value. Now let's derate based on the environment it's going to be in, the ambient temperature. Right? We're going to go to table 5A. Okay, 52 degrees is our temperature with a 90 degree insulated copper conductor. So there is no 52, therefore I'm going to jump up to 55. I know I have a 90 degree rated insulation on my conductor, so I line those two up and I can see I got derate by 0.76. Okay, 0.76. So third step, we're going to solve it. We're going to take our 40 amps and we're going to multiply by 0.76 to get our new value, which is 30.4 amps. Okay, that 30.4 amps, that is your new maximum permitted ampacity on this number 10 because of this ambient temperature. So we went from 40 amps out table 2. Right, table 2 says, oh, number 10 is good for 40 amps, but again, up to 30 degrees max. So because we're over that, we got to reduce the amount of current on the conductor, which thereby reduces the amount of heat that's generated from that conductor. Right, so now the insulation can still safely dissipate the heat without breaking down. Okay, so, oops. All right, one more. I'm going to mix a bunch of everything together now. A big goulash here, we'll call it. So the scenario is we have more than 3 conductors installed in an ambient temperature of 35 degrees. So we're going to combine tables 2, 5A, and 5C all into one. Okay, but regardless, your first step is going to be go to table 2. Let's get our baseline values for these 3 number 10s, which are T90, and our 3 number 12s, T90s. Okay, thankfully they're the same insulation. So again, I believe the number 10s were 40 amps. I'll double check, but the number 12s, was it 25 or 30? Let's have a look here. Number 12, 90 degrees is 30 amps. Okay. So that's your first step no matter what. Okay. Now there's two ways of approaching this. It doesn't matter, you're going to get the same answer. You can knock off, you can derate first because of the number of conductors and then do the table 5A for the ambient temperature, or you can do it the other way. You can solve for the ambient temperature first and then go number of conductors. It doesn't matter, you're going to get the same answer. For me, I usually just solve it as I read it. So my first thing I'm going to do is solve for the number of conductors we have together, right, which is a total of 6 conductors. That is going to bring us to our second step, which is derating based on the number of conductors, which is table 5C. Oops. Okay. Table 5C, 6 conductors. It's going to be the same as our previous two. Number of insulated conductors between 4 and 6, we're going to derate to 0.8, or 80% of table 2 values. Right? 0.8, 80%. Okay, so what I do now is I take my base values. I got a step 1. So 40 times 0.8 and our 30 times 0.8. 8, 16, 32 amps and 24 amps. And for those that wondering how I did that so quick, being not good at math, I'm not afraid to admit that. All I did here is just 8 times 4, 8 times 3, and that gave me those answers. Okay, just a little trick there in case you didn't know that trick. Okay, so I just derated here based on the number of conductors. Okay, consider this your new baseline. What we did above, that no longer exists. This is our new baseline values. All right, so we solved for the number of conductors, but we're not done because it's kind of warm where these wires are going. All right, so our third step, we're going to derate for temperature. Okay, which is table 5A. Okay, so what is our temperature? 35 degrees. Cool. Let's go look at 5A. Down to 5A. So this one, it actually works out nice. You actually do have a row for 35 degrees. But again, if, say, the ambient temperature I told you was going to be 37 degrees, in that case, you'd have to round up and go up and use the 40 degree row. But works out that we have 35 degree row. Perfect. So 35 degree ambient temperature. Our insulation temperature rating is 90 degrees, so therefore we are going to derate by 0.96. Okay, 0.96 or 96%. Okay, so what we're going to do here is now we're going to grab these new baseline values we had and derate those. Okay, so our number 10, which was good for 32 amps. We're going to derate that by 0.96. And our number 12s, which were good for our new value is 24. Same thing, 0.96. Okay, now my head's not that good. There's no tricks on this one. I need a calculator. 0.96, which gives us 30.72 amps. And then for the number 12, 24 times 0.96, 23.04 amps. That right there, folks, is our maximum permitted current that we can put on these conductors in this installation scenario. So we derated for both number of conductors and the temperature rating that it's going to be in. Look how far we dropped from the table 2 values originally. Right? Our number 10's dropped basically 10 amps, and our number 12's dropped about 7 amps. Right? So because we dropped the amperage, we're dropping the amount of current, or sorry, we're dropping the amount of heat that's produced on the insulation. Right? So we're protecting the insulation. When we're doing this, we're protecting the insulation from breakdown, from overheating, right? Because the insulation is designed to dissipate heat. But if we induce more heat onto the insulation than it can dissipate, then yeah, it's going to start breaking down. Okay, so I hope this helps with derating based on number of conductors and as well as the ambient temperature. Okay, so talk to you next time. Any questions, let me know in the comments, and I'll talk to you next time.